Okay, this is a problem that fits into representations of reactions and also limiting reactant, particulate diagrams. So I'm going to walk you through how to solve this one. So it says, consider the mixture of ethanol, C2H5OH, and oxygen shown in the accompanying diagram. Write a balanced equation for the combustion reaction that occurs between ethanol and oxygen. All right, so first, let's write our balanced equation. So let's see. We've got ethanol, C2H5OH, and oxygen. And we know that with hydrocarbons, the combustion of a hydrocarbon is going to give us carbon dioxide and water. All right, these can be some of the most challenging problems to balance, combustion reactions. So the way I start is I balance carbons first. So let's see, put two right here, then hydrogens. So I've got six, two over here. I'll balance that with a three. And then I'll balance oxygens. And really by using a coefficient in front of the O2 is helpful because it only affects oxygen. And I can put any number I want to right there. So let's see, I've got 4 plus 3, 7 oxygen over here. And the products and the reactants have 1, so I just need 6 more. And I'll solve that with a 3. All right, so there's our balanced equation. The second part of this problem says, which reactant is the limiting reactant? All right, so I find it really helpful to use something called like an ICF table, initial change final, when I have particles in a diagram and I'm trying to do stoichiometry as well. So the I stands for initial, and I'll just go through and put how many molecules or moles, they can represent moles as well, of what I'm given. All right, so in this drawing, it looks like we've got 2 molecules of ethanol, 1, 2, 3, 4, 5, 6, 7, 7 molecules of oxygen, no carbon dioxide, and no water. All right, the change is where we're going to say how much of the reactant's used up, how much product is made, and that the change is dependent upon the balanced equation, upon our coefficients that we put in. So the change, I'm going to do this algebraically first before I solve it. The change for number of ethanol moles or molecules, however we are looking at it, would be plus x. Remember, I'm going from coefficients, so that's a 1. The change in oxygen is going to be 3 times that, 3x. The change in, oh, whoops, and I'm putting plus, I mean minus, right? Because these are reactants and we're using them up. And then over here on the product side, we're going to be adding 2, 2 times x for carbon dioxide and 3 times x for water. Again, change should reflect the coefficients and the ratio of the reaction here, 1, 3, 2, 3. All right, so I need to figure out which is the limiting reactant. So if all 2 of these ethanol molecules react, I am going to need, so x equals 2 in that case, then I'll need 6 oxygen molecules. I have that. I've got 7, so that works. So I'm just going to go ahead and go with that. If we use all of the ethanol molecules, then that would leave us with no ethanol molecules. This 3 times 2, because remember, x we decided was 2 here. That's minus 6, so 7 minus 6. We'd have 1 oxygen molecule left over. All right, in this situation, ethanol is the limiting reactant. All right, and then C says how many molecules of carbon dioxide, water, ethanol, and oxygen will be present if the reaction goes to completion. So all we have to do is finish filling out this ICF chart. So over here with carbon dioxide, it looks like, remember, our change, the X, in this situation is going to be 2 molecules. So 2 times 2, that's going to give us plus 4. And then X, remember, is 2 again. 2 times 3 is 6. This is going to be 6. Oh, I don't need to put plus. And this will just be 6. All right, so I'm left with no ethanol molecules, 1 oxygen molecule, 4 carbon dioxide molecules, and 6 water molecules. All right, so that's that problem.